Let us continue the lecture on the cameras, and now we're going to talk about stereo. So there are different types of stereo cameras that are used in robotics, and they could be divided into active and passive type. We as humans use so-called passive stereo. We do not emit any light by ourselves. We have our eyes that are receptive to the field, to the light that is emitted at the end of the day by the sun, and that's it. And there are another techniques. They're used in particular in such systems as Microsoft Kinect and Intel RealSense, those types of cameras. And they rely on the projectors. So they project a certain grid or pattern on the surrounding, typically in the visible part of the spectrum in infrared, in order not to confuse people with this and the other cameras. So they emit some light in the different parts of the spectrum, not visible to humans, and they have cameras with the photosensitivity in this part of the spectrum. So they have a stereo pair, and this stereo pair is capturing the depth in the image, and the normal monocular camera is capturing basically the color. The whole idea of the stereo vision or the binocular vision could be demonstrated again with some waving my hands over here. So try doing the following. Try to close one eye and take a look at the finger and take a look at your finger with another eye. This will basically give you the idea what the disparity is. The disparity is the distance between the pixel position of an object in two different frames. I have my finger slightly off to the left while I'm looking at it with my right eye, opposed to the situation when I'm looking at it with my left eye. And this difference in the position, in the X position, makes me capable of calculating the depth of the object in the scene, because the further I move the finger or the object from me, the smaller the disparity becomes. And at the very limit, at the infinite distance to the object, the disparity is zero and tells us the story behind the far objects being visible worse. So we cannot really tell precisely their depth in the frame, in the scene. If something is at a distance of, let's say, 1 kilometer, you cannot really tell if it's 1 kilometer and 20 meters or 980 meters. So your resolution decays as the distance grows. This basic idea, with two images being slightly different, is the backbone of all the stereoscopic vision, both the active and the passive one. Our robots, and this robot is depicted on the right, our robots were the first in the league to introduce stereoscopic vision. It allows for many cool things like opponent detection and just object detection with the point cloud segmentation. So we don't necessarily have to rely on the assumptions about the geometry of the scene. We can detect the objects just from a single shot from two cameras, left and right. These cameras are identical to each other, and they have their optical axis pretty much coplanar. So they pretty much look in the same direction, as we can make them match. And they have the fixed distance between them. So we know this distance from the model of the robot. It was designed this way. By the rules of the league, we cannot make these cameras move independently to each other. So they have to be fixed, like the normal human eyes are. They look at the same direction. Well, I can tell that, let's say, my finger has a disparity of 500 pixels or 5,000 pixels, whatever. That doesn't give you much. The problem here is that If the distance grows, the disparity becomes smaller, and so what? How can we calculate the distance out of disparity, and can we really do that? Well, it turns that we indeed can, and in order to do that, we need the calibration matrices, we need the base of the stereo, which is the distance between two eyes or two cameras. And while having all of that, we can indeed calculate a so-called depth map. And an example of a depth map is given in the slide on the left. So the main idea behind the depth map is that the closer is the value here, the brighter is the color, the closer is the object, and it's the metrical or more adequate representation of the distance. We can ask for a specific area in the depth map, so we can look for a certain pixel in it, and we will be able to find the distance in real meters, in contrast to the disparity map. Disparity map doesn't give much of that. It's about those disparities that depend on the camera resolution and other things. Depth map works in real measurable distances, so it's a more convenient thing to have. And here on the right, there is drawing a scheme of different distances to the objects and how the disparity is changing. Let us briefly talk about those active infrared cameras that we don't use because they are not allowed by the rules of the RoboCup League. So the main things that we have here is on the very right, this is a projector, and it's projecting a pattern over all its field of, well, not field of view, but field of projecting. And here is the normal RGB camera, 3-channel, regular one. And here we have two identical cameras that capture the scene in the infrared part of the spectrum. So this is the distance here between one and another is the base of the stereo. It's, I can think of like 8 centimeters, 7, something like that. So it allows for the stereo detection, and here in total we have 3 sensors and 1 projector. This whole thing is called Intel RealSense. They come in different models like D435, 55, 415, and they have slightly different cameras. They have rolling and global shutter, and they also have slightly different working ranges. So you can check the Wikipedia page about that. And this camera provides adequate active stereo, real true stereo measured, not like thought of because the Earth is flat. No, that's not the case. This camera provides the measured depth data in the range between, say, 0.5 meter and 6 meters, nearly. That's an average of all the models. The good thing about it is that it's plug and play, so you can just use a single Type-C cable, and it will provide all the power for this camera, for the projector, and for the sensitive modules. And it also has IMU, inertia measurement unit, in some configurations. And also it has a software development kit, so that's a pretty solid piece of equipment. And if your problem allows for that, in contrast to the robotic football, well, that's a good tool to have. One thing that is better here in Intel RealSense, in contrast to the passive stereo, is that it works in dark. While you're trying to distinguish, let's say, dark blue from dark green in HSV color space, and you're trying to find some, well, black cat in a dark room, this camera will allow you to detect all the shapes and distances to the object. And you can segment that, and that is more stable. So you can switch to the stereo mode if in the normal standard part of the spectrum there is no sufficient lighting. But anyway, we cannot use that, so that's just for the context. For each depth map, we can construct a corresponding point cloud. A point cloud is a set of points with 3 coordinates, x, y, z, and they are somewhere in the space in meters, so it's another real-world representation, not a representation that is dependent on, say, camera resolution or anything like that. So one of the normal and fine ways of processing data is the first find out the disparity, then the depth map, and then the point cloud with some further processing, segmentation, whatever else. So those depth maps could be constructed in multiple ways, but the core idea is that we have to find the proper correspondences between the objects in the left frame and the objects in the right frame. And that's the main idea. So if we can do that for one point, we can do it for a number of points, and that will give us the whole picture, the whole depth map. Here you can see the correspondences that I was talking about. Since those lines are parallel, you can tell that probably this matching makes sense. So with these blue dots, we have just the key points marked on this image, and the key points are the points that are distinct from their surrounding, and we will talk about them in more detail later. And those green ones, they are here for the matches that were found between the left image and the right image. And how can you even tell, are they different or they are not? Is it the same image? No, it's not, because let's spot something here. So at first, this strip over here is different from the strip over here. And the excavator here is to the right of this black bar. And here it's aligned with the black bar on the wall. And this object here, this car, is rotated. So here, for sure, that's the left picture, because the left side of this car is visible, and this is the right picture. So here we have 2 pictures. This is a stereo pair. It's aligned horizontally pretty well. And also here we have some areas that are distinct from their surrounding, and the correspondences between some of those points. How can we perform the matching between 2 pictures, left and right? The most straightforward and the simplest, yet time-consuming, but still fundamental way of performing this matching is so-called block matching. We can do the following. Let's suppose that we have 2 images, left and right. Try to spot some things over here that indicate that the left one is indeed the left one. How can you tell? Let's say that the top of this cone is in the middle of the cheek, and here it's to the left of the cheek. So clearly here, the left one is indeed a left picture of the stereo pair. So let's say that we are to find correspondence to this pixel, to the top of this white cone over here in the left frame. What we can do? What can we do? We can extract a patch of this frame, just a rectangle over, just a rectangle nearby the surrounding. And we can then try to move this rectangle in the surrounding of the same coordinates, but in the different image. So we can move it to the left and try to find the best correspondence among the ones that we are considering. The whole idea here is that if we can set the difference in this form, as given in the slide, we will find the best match between 2 patches from one single patch from one image and a number of patches with whom we will compare this one single patch. When the best match is found, we can place, or we can write down this shift in the disparity map or the depth map that will be calculated out from it. So once again, we are cropping a patch from the left image, we are moving it on the right image. When the best match is found, we are writing the shift that gives the best match to the disparity map that we are calculating. That's the whole idea behind block matching. There are certain problems with that. If we have our stereo pair not perfectly aligned, so the angles of inclination of two cameras are slightly off, it will not work properly. If we have, let's say, some glass or some objects that are in the foreground, so they are rotated and they look slightly differently, this block matching could fail to deliver. But still, this is a good method for reasonably easy conditions. And it's perfectly tunable, so that's a good one to keep in mind. Another way to find correspondences is to use so-called key points. I have already mentioned them. Those key points are the points or the areas or the specific pixels even in the frame that are very much different to their surrounding or that are distinct to their surrounding in terms of the distribution of the gradients. Here in the left image, you can see that only the corners, and even not all the corners, are marked here in green. That's because if you're looking at certain objects, or if you're looking at a wall, let's say, the things that you're going to spot are exactly the small dots and maybe, I don't know, maybe a fly that is sitting somewhere. If you are looking at a blank white neon wall, you will be not even able to understand what's the distance to this wall. That's because for the flat surfaces, that matching will not work properly. So out of all the objects and all the surfaces, we are trying subconsciously to spot the distinct pixels or the distinct areas that could be tracked by the second eye. We're trying to find the areas that are visible from both eyes and that we can find in both pictures. That's the whole idea of the key points. And they give us more compact and robust representation of the same scene. We can have, say, 10 megabytes of data, raw data in pixel form, the whole stereo pair. While condensing this whole scene to the key points, we are representing basically the same scene, but in much more compact form. And it makes sense to do so if we are using some sophisticated methods like point nets, or if we even want to segment those pieces of data, those points, by some really complex method that is computationally difficult to perform. So we want to minimize the time that is required for those computations, and we have to use only the data that is crucial to the whole representation of the scene. So key points could help us with that. On the right here, you can see that the majority of the key points are here on the fur of the head, and also somewhere else on the head. And the background has no key points. It has no distinct elements because it is blurred. It's out of focus. And even this point, it comes from some piece of fur from the head. Key points are only at the places where the gradients of different orientations meet each other. That's basically the whole idea of finding them in the picture. We can think of applying the vertical gradient operator and the horizontal gradient operator, and if we happen to find high enough amplitude or intensity of these gradients at a certain point, probably this point is a key point. If we have already obtained those key points, probably we want to match them with the key points from another image, right? If we have found the key points on the left picture, we want to match them with the key points from the right picture. In order to do that, we can calculate the vectors that describe the best the key points that we have found. So the first and the most trivial representation of the key point is its surrounding as it is. So just the whole patch of the frame, and that's it. And why is this representation even bad? Why can't we use it? Well, first of all, it's the same idea as in the block matching, and it's prone to failure for the same reasons. The next thing is that those patch-based surroundings, they are not invariant to scaling and rotation. And that's a problem, because with key points, we can go even beyond just a proper stereo pair. We can do it like it's given here in the slide. We can have a template, a reference picture with an object, and we can try to find this object in just an arbitrary scene with a random scale, rotation, orientation, whatever else. So we can perform object detection, basically. We can find certain objects using key points. And it would be cool to have a tool that is capable of finding not only the vertical, say, objects or books, but the same objects in different orientations. And descriptors provide exactly that. They are the way to describe the surrounding of a pixel in a form that is invariant, or in some sense, up to a certain degree, invariant to the rotation and to changing of the scale. That could be done with the scale invariant feature transform, or some other methods, some other techniques of the same nature. They are basically about constructing the distributions of local gradients in certain subsets of the surrounding of a pixel. And then those distributions are vectorized starting from the dominant orientation of the gradient. So here you can see this circle, and this line over here that is pointing at almost 3 o'clock. This is the dominant orientation of the gradient. The rest of the data in this descriptor will be written in accordance with this dominant orientation. So the whole idea is that if the picture is rotated, if the object is rotated, the dominant orientation of the gradient will be the same. So we will automatically rotate this key point while calculating it on the different image. Regarding the scale, the story is pretty much the same. If we have, let's say, a corner, and we're looking at this corner from a different scale, well, that's still a corner, but it's just slightly bigger. And the distribution of the gradients will be at least similar. The whole idea of descriptors of the key points is to find or construct a proper representation for the pixels in the frame that are distinguishable in the other frames of the same scene. All those stereo processing methods, they have a variety of use cases. One of them is the three-dimensional reconstruction. So, for example, you can take many pictures of yourself with your phone like this, or even the video of yourself. Then all those frames in the form of the point clouds will be stitched together in one 3D model of yourself. With the modern software, you can do that without even any studio-grade filming or whatever. You can do it pretty much on your own if you will find out an instrument or make your instruments with OpenCV. This is totally possible. And if we're talking about robotic football, here on the right, you can see the example of our robot seeing two opponent robots. They are marked in red over here, and they are visible because they are high enough objects that are on top of the field. They are higher than a certain threshold. They are higher than a ball. They are very much distinct. We have fitted a model of a flat surface to this point cloud, and these objects could be detected just because they are separate from the rest of the scene. Also, these approaches could be used to any kinds of 3D modeling or 3D scene processing, such as object manipulation. We can go no further than to my bachelor thesis that was about removing the objects from the foreground. There is a service, Google Street View, so you can virtually travel in different cities, different parts of the world, and there are some objects, people, light posts, and so on, that do not allow for the smooth transitioning between different shooting points. The cars that were filming all those scenes, they make just a single frame in each 5, 10, 15 meters. So if you want a smooth transition, you cannot really do that if you don't have a precise model, and the precise models are not there. If you want to perform a smooth transition, it is necessary to account for the foreground objects. And I was doing exactly that. My whole thesis was about removing the foreground objects, such as dogs, people, and so on, from the stereoscopic images of the streets of different cities. So that's it for the stereo part and for the cameras. Thank you for your attention.